In this presentation, I will talk about what is new in gallium nitride and silicon carbide technologies for power electronics. I am Florin, Udrea, the CTO and co-founder of Cambridge GaN Devices Ltd. Here we have a table with properties, with physical properties of silicon, 4H silicon carbide, gallium nitride, gallium oxide, and diamond. One main thing to notice is that the breakdown field, that is the critical electric field at which the impact ionization results in avalanche, is much higher in all wide bandgap materials compared to silicon, at least 10 times higher. Highlights are also the thermal conductivity for silicon carbide, which is about 3 times that of silicon, and the very high mobility in the two-dimensional electron gas in gallium nitride in the heterojunction structures, which reaches almost 2000 centimeters squared per volt second. However, physical properties are not the only things which are important in commercializing these devices, but we also have to look at system and technology key aspects. In terms of the energy efficiency and performance, all the wide bandgap materials are delivering great advantages compared to silicon, and that's why I gave silicon a red light here. Also, silicon carbide, gallium nitride, diamond, and gallium oxide can be made much smaller for the same on-state resistance, which means you can increase the frequency at which these devices can be driven, and that results in a smaller form factor of the entire system, because the passives can be shrunk, the inductors and the capacitors around the power devices can be shrunk, and the total form factor of the system can be reduced significantly. In terms of reliability, silicon carbide and gallium nitride have made tremendous progress in the last decade, and that's why they have now a green light here. And not the same thing can be said about diamond, and gallium oxide still suffers from very poor thermal conductivity, and this is the reason I gave a red light here. Ease of manufacturing, infrastructure, and cost are good attributes of gallium nitride, which can be made on silicon, and in a way matching the infrastructure, the manufacturing, and the cost level of a silicon. Silicon carbide still has to catch up in all these 3 categories. Ease of use, silicon carbide has improved a lot. There is an insulated gate that is very similar to silicon, and gallium nitride is catching up. In fact, in CGD we are developing such a technology to make the device to be easy to use in all kind of applications in power electronics. Diversity, silicon carbide and GaN still have to improve. There are 2 devices. There is the power MOSFET in silicon carbide and the HAND in GaN, but these 2 devices are finding a range of other devices in silicon, from power ICs and LD MOSFETs in lateral structures, all the way to gate commutative thyristor in the very high power domain. And in between, we have superjunctions, we have IGBTs, we have bipolar junction transistors. So a variety of such devices that silicon carbide and gallium nitride have to fight against. Now, the evolution from vertical silicon power MOSFET to vertical silicon carbide MOSFET has been quite spectacular. The drift region has shrunk by more than 10 times and is 50 times more conductive, resulting in 500x reduction in the on-state resistance. One of the problems with the technology still remains the very low channel mobility in silicon carbide. The interface mobility is only around 20 centimeters squared per volt second, much smaller than in silicon, which is around 1000 centimeters squared per volt second. For this reason, we have the trench gate geometry, but having these multiple trenches inside the device also increases the gate to drain and drain to source capacitances, which is undesirable. Evolution from lateral silicon power LD MOSFET to lateral GaN HAMD is equally spectacular. Silicon LD MOSFET is based on the research technologies, and the dimensions were very large. Now today in GaN we still have a lateral technology, but we replace this end drift region here with a 2-dimensional electron gas, which is 100 times more conductive, and the drift region has been shrunk more than 10 times at the surface. we can deliver with this more than 1,000 times reduction in the on-state resistance. So today the gallium nitride HEMT is significantly better than the silicon LD MOSFET in the 1990s in terms of performance, in terms of the form factor of the device itself. So what is new in silicon carbide and what is the future in silicon carbide? I can see two avenues very interesting to explore, the FINFET and the superjunction. The FINFET is based on shrinking the pitch between two adjacent cells, two adjacent trenches in a power MOSFET. If we could do that, then the depletion regions which are formed in the P body here can join, and now the charge balance will dictate that the charge in the channel is now increased because the depletion region obstruct each other to further grow. One can imagine a situation where the channel is so small, it's of the level of tens of nanometers, where the depletion region completely disappears and all the charge in the gate now is balanced by the charge in the channel. This is called bulk inversion, where the channel is formed within the whole body of the P. The advantage of this is that the channel moves away from the interface towards the bulk and the mobility is increased, and on top of that we have an increased charge because of the absence of the depletion region. Now, the advantages of the FINFET compared to a standard MOSFET can be summarized here: increased electron charge, bulk inversion, and higher physical mobility. And also we can have lower transverse electric field, which leads to less scattering and increased mobility. All of this lead to lower on-state resistance. This has been published extensively in the ISPSD conference, the main forum of power semiconductor devices. We have made this structure. In fact, we have just published this in ISPSD 2022, where the pitch between two trenches has reached 144 nanometer, at which level the depletion regions join together, and now we have an increased channel charge, and we have increased mobility as a result. The performance of it is 1 kilovolts with an on-state resistance of 0.7 milliohm centimeter square, and this is a normally off device with a threshold voltage of 2.2 volts. As far as I'm concerned, this is the world record for a trench MOSFET structure. Now, another possibility is to apply the silicon carbide superjunction concept. If the FINFET was very useful, very efficient at the lower voltage to decrease the channel resistance, superjunction can be very useful for higher voltages to increase the conductivity within the drift region. So here we can form alternate pillars of N and P by multiple implant and epitaxy, and this is a very nice result from this Japanese group published in IDM 2018, where they achieved 1.1 kV with an on-state of only 0.63 milliohm centimeter square. What is new in gallium nitride? Well, we see a number of companies doing integration, monolithic integration, and turning the HEMT into a power integrated circuit. And we also see multi-channel technology coming into at least at the research level, at a very advanced research level, and hopefully this will be towards production in the future. In terms of the monolithic and integrated solutions, in the past we used to have the cascode, which is a hybrid integration between a silicon MOSFET and a depletion mode HEMT, and this device has the advantage of delivering the reliability of the insulated gate of silicon. An alternative solution to that is the smart HEMT, the ICE GaN HEMT, proposed by our company, CGD. And here we have a smart auxiliary interface, which delivers a very high gate voltage protection and delivers a number of sensing and protection features like the current sense. Another possible solution, in which we call level 2 monolithic integration, is to integrate the entire driver within the GaN chip, the gallium nitride chip, and the advantage of this solution is to cut the parasitics from the driver to the power device. However, this solution may have problems in terms of scaling at high power because the power device can actually hit the driver and becomes inefficient at very high power levels. So here is a little bit about ICE-GaN. The ICE-GaN, Integrated Circuit Enhancement GaN platform, is based on monolithic integration of smart features with together with the power device. Is a proprietary technology from Cambridge GaN Devices. Cambridge GaN Devices is a fabless semiconductor company. It's a startup from University of Cambridge in a scale-up phase. The multi-channel technology is also very interesting. Here we have a structure which incorporates a number of GaN-AlGaN layers forming multi-channels on top of a sapphire substrate. And to be able to control this multi-channel, which is actually the challenge in such a device, we use a single channel in a cascade configuration here. So the single channel here is an insulated gate channel which controls the depletion mode multi-channel hand. All, however, is integrated in a single chip. The result is quite impressive, achieving 10 kilovolts is 40 million centimeters square with a threshold voltage of 1.5 volts, so normally of operation. This is a world record. I don't know of any devices that can operate with a lateral geometry at this kind of voltages. So power devices present and featured. The bulk today is based on silicon solution, power MOSFET, superjunction, trench IGBTs, but the fast growing market today are all based on wide bandgap materials, gallium nitride, and silicon carbide. And here we have normally of GaN HEMT, different solutions from different companies with different levels of integration. And we also have the silicon carbide power MOSFET in planar and trench technology and the silicon carbide Schottky diode. The future will be bright. We'll see still evolution from silicon. We'll see perhaps three-dimensional types of superjunctions. We'll see superjunction IGBTs, but we'll also see a lot of interesting and new solutions in silicon carbide, including silicon carbide superjunctions and FINFET technology, and a lot of GaN, including multi-channel GaN, GaN power ICs, and possibly vertical GaN. Thank you.